Hi, this is Brad, and welcome back to the Analog Universe. This is episode 8, the Michelson Morley experiment. So I imagine there's two kinds of viewers out there right now. Those that are asking, who are Michelson and Morley? And those who are asking, what took you so long to get to the Michelson and Morley experiment? So Albert Michelson was a physicist in the mid to late 1800s who measured the speed of light to within 30 miles per second. At the time, this was amazing, and it brought him quite a bit of fame. Edwin Morley was a scientist, lived around the same time, and he was the first one to measure the atomic weight of oxygen. And so in the 1880s, they were both relatively famous scientists. Then, in 1887, they got together to see if they could achieve Albert Michelson's big idea. So he had gained considerable fame in measuring the speed of light, but the true holy grail for physics at the time was to prove that the ether existed. Now, the ether at the time was pretty much assumed by almost everybody to be a medium out there in the universe that pervaded all of the universe and served as a medium to propagate light waves. That's how light waves traveled through this ether, just as water waves travel through the medium of water. If they could prove the existence of ether, that would be huge and win them everlasting fame. So the measurements necessary to determine if light was slowed down by this ether would be far, far finer than even Albert Michelson could measure at the time. So he came up with a machine that he thought would do it. He called it the interferometer. So in the 1880s, he and Edwin Morley got together and created their interferometer. This was a machine that wouldn't measure the speed of light accurately enough to tell whether it was slowed down by so many meters per second. But what it would do is measure whether the ether wind, as it was known at the time, could knock light waves out of phase. So here's how it worked. With the interferometer, there was a light source that directed a beam of light to a half-silvered mirror. The half-silvered mirror allowed half of the light to go straight through the mirror, and it reflected half of the light at a 45-degree angle. So the light went out from the light source, half went straight, and then returned back to the half-silvered mirror, and then the other half of the light went at a 45-degree angle, the same exact distance, and was reflected back again to the half-silvered mirror, which then reflected both beams of light to a detector. And each leg of this journey the light took was exactly the same distance and far enough that when the light finally got to the detector, that if the light that had been traveling perpendicular to the light beam that went straight traveled a longer distance, then the two light beams would be out of phase. That is, the peaks of the two waves would arrive at the detector at very slightly different times. And instead of seeing a steady light, what you would see is an interference pattern, like the interference pattern that we talked about when we discussed the double slit experiment. Okay, so Michelson's theory was this. The Earth is traveling at a fairly good speed around the sun through this ether field. Therefore, what we should be feeling is what was known at the time as the ether wind. The ether would be flowing against the Earth as it traveled in one direction around the sun, and with the Earth when it traveled the other direction around the sun. Okay, so if you were to catch this, when the ether is flowing against the Earth and not with it, then it should affect the speed of light ever so briefly, but enough to cause that interference pattern on Michelson and Morley's interferometer. So they tested the speed of light when the Earth was going this way around the sun and when it was coming back that way around the sun. And the experiment should have worked like this. The light that went straight from the half-silvered mirror would be flowing against the ether wind. The ether wind here is represented by the little green arrows. And then when it was reflected back to the half-silvered mirror, it would be flowing with the ether wind. I suppose their idea was that it would be slowed down as it was flowing against the ether wind to the same degree that it was sped up with the ether wind. So that would just be the regular speed of light that was measured when it went from the stationary mirror to the half-silvered mirror. The light that went at 45-degree angles, however, would have the ether wind flowing perpendicular to it. And then again, when it was reflected back, it would have the ether wind flowing perpendicular to it. So rather than going straight to the moving mirror and back, what you would get is light that was blown slightly off course, if you will, and it would strike the moving mirror slightly to the left of where it would hit the moving mirror if there was no ether wind. And again, of course, when it was reflected back to the half-silvered mirror, it would continue to be blown, for lack of a better term, off course by this ether wind. So the idea that Michelson had is that the distance that this light would be blown or moved off course or from directly straight to the moving mirror and back, the distance represented here by the blue arrow, and of course I'm exaggerating a bit to show the point. So this blue arrow represents how much further the light traveling perpendicular to the light beam that went straight traveled. This perpendicular beam would travel, according to Michelson and Morley, further by this distance. Not enough to measure exactly, but enough to create an interference pattern. So Michelson and Morley used their interferometer to measure the speed of light and whether it created this interference pattern when the Earth went this way around the sun and that way around the sun. And they tried various configurations. And again, if they could prove the interference patterns, they would be famous and their place in physics history would be assured. Well, their place in physics history has been assured, but not for what they thought they would prove, because they found no interference pattern no matter how they pointed their interferometer, whether they measured it going this way around the sun or that way around the sun. And the conclusion was, there's no ether. This was huge. It's impossible to overstate how this hit the physics community. And this was 1887, just 20-some years before Einstein came up with his special theory of relativity. And during this time, the physics community was rocked. If light doesn't travel in waves through some kind of ether, then how does it travel? So it was into this theoretical vacuum that Einstein found himself at the turn of the 20th century. When he started looking at black-body radiation and Maxwell's equations of electromagnetism, he came up with special relativity. And when Arthur Eddington confirmed that Einstein's prediction from general relativity regarding the light of the star behind the sun being bent during the total eclipse, then the physics community sustained a second major shock 20 years later. But again, that was all set up by Michelson and Morley's discovery, or their belief that they discovered that there was no ether. But again, as we discussed in episode 7, if there is this interstellar medium that acts to propagate light waves, then undoubtedly it's not just a field that the Earth flows through, or even a wind that's blowing against the Earth one way around the sun and with the Earth the other way around the sun. But rather, it's flowing down to the center of the Earth. And up is a direction that Michelson and Morley never tested with their interferometer. So maybe there is this interstellar medium, maybe there isn't. But Michelson and Morley couldn't have proven it either way unless they had pointed their interferometer up, which is not a direction that they pointed it. So this conclusion that physicists have arrived at ever since 1887, that Michelson and Morley proved that there was no ether field, is not necessarily correct. It hasn't been proven to this day one way or the other. Adherents of the theory of relativity will tell you, oh yeah, it has, relativity has proven that. But that gets to the other issues that we've been talking about in this series. So is there this subatomic medium out there, these some particles that we have referred to them as previously in this series, that serves to propagate light waves? Again, it's been since 1887, and because physicists thought that this was proven, they haven't looked further. Just saying. Maybe it's time to continue our search. So we'll see you next time when we talk about possible ways to find some of the proofs that we've been talking about in this series. See you then.